Hello, students. Today we'll be working on one last analysis before we start to pull all of the different things together that we've been looking at. This analysis is what it takes to have horizontal asymptotes. So we're going to look at the limits as x approaches either positive infinity or negative infinity. So just remember you're looking at on as x approaches positive infinity, that would be on the far right hand side of your graph, so on the far right. And as it approaches negative infinity, we'd be looking at the far left hand side of your graph. And this is nothing more than just a horizontal line, y equals a number. So what is the y doing on the far right-hand side of the graph? And then what is the y doing on the far left-hand side of the graph? And then we're going to look at a couple of definitions about limits at infinity. So if you have a constant and that constant is divided by a base to a power, and that base approaches infinity. So basically, you have a number over infinity, even if it's infinity to a power. Then, according to this definition, that limit is equal to 0. Think of that as your chances of winning the lottery. If you have even 5 chances out of an infinite number of chances, that's essentially no chance. So you have that equaling to 0. The same would be true for negative infinity. So if you have a number over infinity, even if it's infinity to a power, that equals 0. And so we're going to use these two ideas to look at some functions and find out whether those functions have limits at x equal or as x is approaching infinity. And if they do, then that would be an indication that we have a horizontal asymptote for that function. So notice that this is going to be happening with rational functions. So these are going to be functions that have fractions in them. So what we're going to be looking at is we're going to always start with direct substitution. But in doing the direct substitution, if we end up with infinity over infinity, then we can start over. And a method that we can use is divide the numerator and the denominator by the highest power of x in the denominator, and then evaluate. So I'll show you what I mean. For example, 1, if I plug in infinity right away, then I would have negative 2 times infinity plus 3 over 3 times infinity to the third minus 1. Well, no matter what I do to infinity, whether I multiply it by negative 2 or whether I raise it to a third power, no matter what I do, I'll end up with infinity over infinity, and that's an indeterminate. So we would say that we would need to do something else with this. So since that is indeterminate, I'm going to start over, and I'm going to use this method that I described, where I'm going to divide by the highest power of x in the denominator. So the highest power of x is x to the third power. So I'll do the limit as x approaches infinity. And I'm going to divide each term. So 2x over x to the third plus 3 over x to the third. And then over 3x to the third over x to the third minus 1 over x to the third. And then we will simplify. So the limit as x approaches infinity. And so we get negative 2 over x squared plus 3 over x to the third. And in the denominator, we have 3 minus 1 over x to the third. Now, when I substitute in infinity for this, I have negative 2 over infinity squared plus 3 over infinity to the third. And this is over 3 minus 1 over infinity to the third. Well, all of these that have infinity in the denominator and a number, a constant in the numerator, that would follow our definition that we had about a constant over infinity to a power. And so what we have is negative 2 out of infinity, that's 0. And 3 out of infinity is also 0. So we have 0 plus 0 in our numerator. And then in our denominator, we have 3 minus 1 over 0, or 1 out of infinity, that would be 0. So 3 minus 0. And that's going to be 0 over 3, which is 0. So we end up with 0 for this limit. And therefore, this rational function would have a horizontal asymptote at, so I'm just going to abbreviate that. It would have a horizontal asymptote. Remember, that's y equals a number, and it's whatever we got for that limit. So the horizontal asymptote for that rational function would be y equals 0. All right, I'm going to move on to problem 2. It's similar, and I'm not going to show it this time, but if I were to substitute in infinity for both of these x's, I would end up with infinity over infinity indeterminate. So I'm going to use that same method I used on problem 1. I'm going to take the limit as x approaches infinity of negative 2x over x plus 3 over x. And I might explain one more time why I'm using an x. I had to use the highest degree of variable from my denominator. So my denominator had an x in it. That was my highest power. And so everything had to be divided by an x. All right, so now that takes us to the limit as x approaches infinity. And negative 2x over x will just be negative 2 plus 3 over x. Now that turns out to be 0 when we, actually, wait a minute, I haven't substituted yet. So a little bit ahead of myself there. So 3 over x. 3x over x, that'll just be 3. And minus 1 over x does not simplify. So I will leave that. Now I'll substitute in infinity. And so I'll have negative 2 plus 3 out of infinity and 3 minus 1 over infinity, or I like to think of it as 1 out of infinity, which is a 0 chance. And so you end up with negative 2 plus 0 over 3 minus 0, and that gives us negative 2/3. So if we were to have an analysis on this function, this rational function, we would say that it does have a horizontal asymptote at y equals negative 2/3. All right, and then our third problem, again, if I were to substitute in infinity, I'd have negative 2 times infinity squared plus 3, and then 3 times infinity minus 1. So again, infinity over infinity, indeterminate. So now I have my highest power of x from my denominator is an x. So I'm going to divide every term by x. So this will be the limit as x approaches infinity, negative 2x squared over x plus 3 over x. And then the denominator 3x over x minus 1 over x. So I'll do a little simplifying. The limit as x approaches infinity. So negative 2x squared over x, that's negative 2x plus, and I can't simplify this, so 3 over x. And then 3x over x is just 3 minus 1 over x. So when I substitute in infinity this time, I get negative 2 times infinity plus 3 out of infinity, that would be 0. And then this is over 3 minus 1 out of infinity, and that would be 0. So I have negative 2 times infinity over 3. And even if you take infinity and multiply it by something and divide it by something, you still have infinity. So we just want to take a look at the sign. The fact that it is negative over positive makes it negative, and what we have is negative infinity. So I want to remind you, this does not have a horizontal asymptote, but we can describe the end behavior that this limit, even though this limit does not exist, it can be described as negative infinity. So on this right-hand side, as x is approaching infinity, y will be approaching negative infinity. So it will not have a horizontal asymptote, but the y will be approaching negative infinity. All right, so I'm going to have us turn to the back, and I think you'll be pleasantly surprised that if you look at what I have on the back, I have a little explanation that will let you avoid having to do all of this algebra that we just did. So I wanted to show you what is going on here, but actually there's a nice shortcut that you can use. And if you'll turn to the back of your notes, that's where we'll pick up.